Today we're going to finish up section 9.2, test about a population proportion. After this section, we should be able to check the conditions for carrying out a test about a population proportion, conduct a significance test about a population proportion, and in particular today we're going to do a two-tailed test, and also construct a confidence interval to draw a conclusion about a two-sided test about a population proportion. Okay, today we're going to look at a two-sided test. Yesterday we had done a one-sided test. According to the Center for Disease and Control and Prevention, 50% of high school students have never smoked a cigarette. Taeyeon wonders whether the national results hold true in his large urban high school. For his AP Statistics class project, he surveyed a simple random sample of 150 students from his school. He gets responses from all 150 students, and 90 say they have never smoked a cigarette. What would his conclusion be? Give it appropriate evidence to support your answer. Okay, we're going to run a two-sided test for proportions here. First, set up the parameter. The parameter of interest is the actual proportions of students who say they have never smoked cigarettes. The null hypothesis is based on the CDC site that 50% is the null, so P is equal to 0.50. Alternative hypothesis would be P does not equal 0.5. He doesn't care which direction, if there's more or less. He's just worried about a difference. And that's what makes this a two-sided test. Again, we need to check the conditions. First, randomness. The survey did a simple random sample of 150 students from a school. Normal. N times P naught and N times 1 minus P naught end up being 75 and 75. Both are greater than or equal to 10, so we're safe doing our normal calculations. Independent, we are sampling without replacement, so we do need to check the 10% condition. So if he's at a large high school, we're going to assume that there's more than 1,500 students at their high school. Name of the test is a one-sample z-test for proportions. To be able to carry this out and come up with a test statistic, I need the p-hat value. So p-hat is going to be, which is 0.6. That's his point estimator. So then to calculate the test statistic, z would equal p-hat minus p-naught divided by the square root of p-naught times 1 minus p-naught divided by n. You can see where p-hat is our 60% or 0.60, p-naught is 50% or 0.50, and the number in the sample was 150. The z-score, or z-statistic, ends up being 2.45. Now I need to obtain the p-value. To compute this p-value, we find the area in one of the tails and double it. So I'm going to find the probability that z is greater than or equal to 2.45. When I do that, I get a 0.0071 area. The area is under the right tail of the distribution. So what I would need to do is double that area, because there's also an identical tail below negative 2.45 in terms of that being a z-score. So when I double that, I end up with 0.0142. Since our p-value of 0.0142 is less than our chosen significance level of alpha is equal to 0.05, we have sufficient evidence to reject the null hypothesis and conclude that the proportion of students at the school who say they have never smoked differs from the national average of 0.50. Now let's talk a little bit about why confidence intervals give us more information. The results from a significance test basically tell us to reject or fail to reject the null hypothesis. When we reject the null hypothesis, we're wondering what actual value the p would have. A confidence interval will shed some light on that issue. Back to the example. Remember, he found 90% or 90 of the simple random sample of 150 said they had never smoked a cigarette before. Before we construct a confidence interval for the population proportion, again, we should check both the number of successes and failures to make sure there are at least 10. But actually this time I need to calculate it with 0.6. So 0.6 times 150 and 0.4 times 150 ending up giving us numbers greater than or equal to 10. So if you remember back from the previous chapter, chapter 8, on how to construct a confidence interval, it's p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n. P hat value in this case is 0.60 again, 90 divided by 150, and our 95 critical value is 1.96. When we substitute that in, we get an interval from 0.522 to 0.678. And again, our conclusion in context would be we are 95% confident that the interval from 0.522 to 0.678 captures the true proportion of students at Tayons High School who say that they have never smoked a cigarette. There is a link between confidence intervals and two-sided test. The 95% confidence interval gives us an appropriate range of P0 values that would not be rejected by a two-sided test that the alpha is equal to 0.05 significance level. The link isn't perfect because the standard error used for the confidence interval is based on the sample proportion, while the denominator of the test statistic is based on our P0 value from the null hypothesis. So in taking a look at this sampling distribution, a two-sided test at significance level alpha, let's say alpha is equal to 0.05, and a 100 times 1 minus alpha percent confidence interval, which would be 95% confidence interval if alpha was 0.05, gives similar information about the population proportion. 95% of the area between the two critical values gives an area of 0.05 in both tails. So that's the two-sided test. 0.025 here, 0.025 there, adds up to our 0.05. If the sample proportion that we take falls in the fail to reject region, which would be between, in this case, 0.42 and 0.58, the resulting 95% confidence interval includes the P0 value. In that case, both the significance test and the confidence interval would be unable to rule out P0 as a plausible parameter value. However, if the sample proportion falls in the reject the null hypothesis region, this is the case here, the resulting 95% confidence interval would not include our P0 value. In that case, both the significance test and the confidence interval would provide evidence that P0 is not the parameter value. Again, the main difference in a significance test, you're basically just trying to reject or fail to reject a given null hypothesis. In a confidence interval, you're trying to find what are the plausible values of the population parameter. As a summary for section 9.2, what we've learned. Again, we always need to check three conditions, random, normal, and independent, before we carry out a significance test. Our test statistic for a test about population proportions is z is equal to p hat minus p0 divided by the square root of p0 times 1 minus p0 divided by n. The one sample z-test for proportions is approximately correct when the data are produced by randomly sampling, 2, the population is at least 10 times as large as the sample, and n times p0 and n times 1 minus p0 are both greater than or equal to 10. The acronym PHANTOM can be used to carry out a significance test. P stands for parameters. H is hypotheses. A are your assumptions and conditions. N is choose the appropriate name for the test. T is test statistic. O stands for obtain the p-value. M, make a conclusion. and S is a statement in context. As long as you follow the phantom steps, you will be okay in calculating a significance test. And finally, confidence intervals provide more information than significance tests do. Namely, a range of possible values for the true proportion parameter P. A two-sided test of H0, where P is equal to P0, at a significant level alpha, gives roughly the same conclusion that a 100 times 1 minus alpha % confidence interval would give. This is the end of talking about taking tests about population proportions. Section 9.3 will cover tests about population means.